All right. So today, this week, we'll be covering breadth-first search, depth-first search, and grid searching flood slash flood fill. So in last week's lesson, we talked about the basic concept of graph theory, but I didn't really tell you too much on how you would use graph theory, I guess. In today's lesson, we'll be starting to talk a bit more about graph theory and specifically, the applications of graph theory. So typically, when you're being involved with graph theory, when you're getting involved with graph theory, you'll have to search through a graph. Whether that's determining whether or not there's a path that exists between two vertices, or determining a shortest path or whatever. We'll need to search through this graph. We won't cover too much about complex algorithms about like shortest path on a weighted graph, pruning a tree. Those are complex things that sound complicated, and I won't be covering too much about those for now. However, we'll start with the basic fundamentals of searching algorithms on a graph. Searching algorithms of graph theory. So the two searching algorithms of graph theory are breadth-first search, shortened as BFS, and depth-first search, shortened as DFS. So let me start with breadth-first search. So breadth-first search, also known as BFS, simply speaking, is a searching algorithm, as the name implies, where it searches breadth first. So let me get up a whiteboard, all right? So you guys know the definition between breadth and depth, right?
I don't know what breadth means.
So breadth means, the definition of breadth is wide, all right? So this is just last week.
Okay.
Yeah, that's what breadth means. Breadth, it's not some complicated comp sci terminology. It's a general English term, and it just means wide. So like, if I want to learn like a breadth of knowledge, like breadth of topics, it means I'm covering. No, no, it's not breakfast. We here at Massey, we will commonly just refer to breadth-first search as breakfast search, since it's commonly mistaken as breakfast. So I might refer to it as breakfast search on accident. But breadth-first search is you're trying to cover as wide of an area. That's what breadth means, and you're covering, and it's just covering more things. So let's say we have this graph here, right? What breadth-first search is is that if we start at some vertex, it will like start by like starting small and just like branching out and constantly just branching out like that. So it will only go deeper once we search through one level at a time. So the distance between like 2 from 1. We'll start searching all the vertices that are the one distance away from this given vertex, and then we'll go to two edge distances away from a given vertex, then 3 edge distances, and so on and so forth. And that's the idea of breadth-first search. It tries to cover a larger breadth of vertices. Does that make sense? And here's a visual that like lets you understand how BFS works. So we first search this first vertex, right? Then we search all the vertices that are connected to that one vertex. So we search 2, 3, and 4 in that order. Then we search those vertices. We go one more step further. We go search this 5, 6, 7, 8. All right? And then once we search all of the vertices, we search one more step further. 9, 10, 11, 12. And that's the idea of breadth-first search. It tries to cover a wide range of vertices first, rather than like trying to find this path, like rather than going like down each path like that. All right. So in this visual, the number on the vertices represent the order in which they're searched. So it searches the first vertice, of course. Then it searches the next the vertices that are connected to it, and then from there it will then search all the vertices connected to those vertices, and then it will then search all the vertices connected to those vertices, and it's just a constant path like that. And since this searches only one step at a time, so it only searches up to a certain depth from a node, we can guarantee if we use the searching algorithm, it will help us find the shortest path of an unweighted graph. Since, let's say we want to find the shortest path from one vertex to another. Since we're only searching one step at a time, pretty much, like one depth, okay, we're only searching one distance away, then we're searching 2 distance away, then 3 distance away. We can then guarantee that we will find the shortest path. Since once we find that vertex, we can just stop. We don't have to go any further, and then we can guarantee, hey, oh, let's say there's we found this first vertex 3 edges away. We can guarantee that it will only take 3 edges to get to this vertex, since it goes 1 step at a time, and we don't have to worry about going 4 steps, 5 steps, and so on and so forth. All right. And to implement BFS, we have to first talk about this data structure called a queue. All right. So with BFS, you'll need to learn what a queue is. And as the name implies, it's like a queue in real life. So let's say we had a lineup of people, let's say we all wanted to go grab burgers at a restaurant or something like that. And there's a lineup of people that needs to be served before that wants to get served. You would typically, if you're nice, calm, and courteous, you would line up, you'd join the line in the back, and then the restaurant would take people from the front of the line. And this is known as the principle as first in, first out, where the first person into the line will be the first one out. Right? And that's also how queues work in real life. Let's say I wanted to line up to grab a bite to eat at Tim Hortons or whatever. I'd line up, and then I'd wait my turn for everyone in front of me to go, and then I'll eventually become the first person in line, and I'll go. And then people behind me will have to wait my turn. And that's how queues work. And we can use a bit more terminology to denote things. So we have NQ and DQ. So a bit of etymology, and meaning adding something and adding to the queue, and DQ meaning removing something from the queue. And so we DQ something from the front and NQ something to the back, because that's how queues work in real life. So to use a queue in Python, you will need to import it, since it's not in Python by default. And here's how you create a queue. So first you have to import queue into Python, and then you have to initialize a variable with queue.queue with parentheses. And then that creates a queue. However, we need to put items into that queue and to retrieve items from the queue. And to do this, we can use .put and .get. So we can create a queue for the previous code here, and then .put adds something to the queue, and then .get removes from the queue. So if we add 1, and then we add 10 to the queue, if we print a queue.get and then print a queue.get, it should print 1 first, since that's the first thing that showed up, then followed by 10. All right? And the thing is, with .get, it will remove the element from the queue and return it. And it will advance the queue. So you'll also need to double check if a queue is empty. And this is where .empty comes in. Well, it returns whether or not a queue is empty. All right? And you don't want to be grabbing something from a queue if it's empty. And you also want to check if a queue isn't empty. All right? So to implement a BFS algorithm, we need to know which vertices are adjacent to each other, as well as which vertices have been searched. Since you don't want to backtrack while you're searching. If you were able to backtrack while you're searching, then you would just end up with an infinite loop, and it'll take you much longer before you find your answer. As well as what vertices to search for, which you can use a queue, since you can search all the vertices in a certain order. So generally speaking, this is how the BFS algorithm looks like with an adjacency list. So first we have to initialize a queue, All right. And we have to put our starting vertex into the queue. It doesn't have to be from it doesn't have to be 0, but I just used 0 as an easy way to visualize this. And here, we have to set all the vertices that we will visit as false. All right. So I created a list with all the vertices that are being visited as false, except the starting vertices, since we don't want to backtrack. We're already visiting the starting vertices, so we don't have to. We can just initially say the starting vertice as true. And we have to check, is there any more vertices to search for? Because if there's no more vertices to search for, we stop searching. So we check, hey, is the queue empty? If the queue is empty, that means we've exhausted all the vertices to search for, and we can't find. And generally, that means we can't find the other vertices. That means there's no possible path to that location. So first, we have to check, hey, have we searched for this vertice yet? All right. And if we haven't, then we have to check if we haven't, there's no more vertices to search for. While that's happening, we check, hey, we get the first thing we have to search for in the queue. All right. And we check, is this the destination? Because if we found the destination, we're gonna stop searching. There's no point in continuously searching this algorithm. All right. And if we have reached our destination, then we just stop. Break the loop. Now, what if we haven't searched? What if we haven't found our destination? Then we have to check all the possible vertices, all the adjacent vertices to this vertex that we're searching. And if we check, hey, have we visited this location before? If we haven't, then we have to search it since we haven't visited before. And we said, hey, okay, we'll visit this location. So we set it to true, and we will put this vertice into this queue. All right. And the reason why, BFS uses queues is, let me just draw it out. All right. Let's draw out this graph here. All right. So we have 1, 2, 3. Actually, let me just undo. Whoops. So we have 1, 2, 3. Let me just give me a sec. 1, 2, 3, 4, and 5, 6, 7, 8, 9, 10, 11, 12. All right. So first, we add the starting position into queue. All right. So we have a queue here. All right. And it starts with 1. All right. And then we start the loop. All right. We go back to the loop. We grab this first one here. Like, hey, okay, let's remove it. Let's grab it. Now we set the current is 1. All right. And then we remove it from the queue. Check, is this the destination? Well, let's just search. Let's say we're searching the whole graph, so there is no destination. And we check, hey, what are all the vertices adjacent to it? Let's also set this to be visited. So let's also put visited, right? So let's cross it out if we visit it. Let's check. Hey, which vertices are adjacent to this queue? 2 is adjacent, 3 is adjacent, and 4 is adjacent. All right, let's add them to the queue, and we haven't visited those. So 2, 3, and 4. So we add those to the queue. All right, and we're done. So we've added all the ones that are one edge, just one distance away from the graph. All right, now we're done. Now we check. Hey, is the queue empty? Oh no, it's not empty. We have more. We have more vertices to search for. All right, let's grab the first thing from the queue. 2. Okay, we set it to 2, and we also have to set these to visited so that we can't search back through these. All right. And okay, we set the current to 2. All right. So we have the current to 2. What do we do? And we check, is this the destination? And since we're not worrying about the destination for now, we just check, hey, let's go through all the adjacent edges, all the adjacent vertices. All right. So from 2, you can go to 1. Oh wait, we've already visited 1, so there's no point in searching 1 again since we've already visited it. Okay. Let's go to the other vertices. 5. Oh, we haven't searched 5. Okay, let's set it to searched, and we'll add it to the queue. All right, and that goes in order. All right, then 6. We haven't visited yet. Let's add it to the queue, and let's set it to visited. All right, and then we're done with that. Then we go to 3. Okay, we go to 3 now. So 3, with 3, we're at 3 now. And we remove it from the queue. Check if it's a destination. And since we're not caring about the destination, it's fine. It's fine. And then we check, hey, what, let's look through all the adjacent edges, vertices. Oh, there's only one adjacent vertice. And we visit it. Oh, there's nothing to add to this list. Oh, okay. We're done. Let's go to the next step of this loop. Oh, we're not empty yet. Let's keep searching. 4. Let's set current to 4. And then we remove from the queue. All right. And 4. Let's look at all the adjacent vertices. All right. From 4, you can go to 1. Oh wait, we've already searched 1. There's no point of adding 1 to the queue again since we've already searched it. Okay, let's look at all the other vertices. I can go to 7. Let's add 7 to the queue. And I can go to 8, and I haven't searched it, so we can add 8 to the queue. And then we also set those to visited. All right. And then from 5, okay, we start over again from 5. Okay, we set current to 5, remove it from the queue. And 5, let's search through 5. Okay, I can go to 4. I can go to 2. Oh wait, 2 has already been searched. There's no point of going back to 2. I can go to 9. I haven't searched it. Let's add it to the queue. And then we add it to the queue, and we set it to visit. We can go to 10. Let's add 10 to the queue. And since we're going to visit, we can add it to visit. All right, and that's done. Now we can go to 6. All right, 6, we remove it from the queue. Okay, and we check all the adjacent vertices. I can go to 2 from 6. But wait, I've already searched 2. There's no point of searching 2 again. So we just stop here. I'm like, okay, 2's been searched. We're done. And there's no other adjacent vertices, so we can stop. So 6 is done. Now we go to 7. Okay, let's set the current to 7. And let's see all the adjacent vertices that we can go to. All right, from 7, we can go up to 4. Oh wait, you've already searched 4. There's no point in adding 4 back to the queue. From 7, we can go to 11 though. 11 hasn't been searched, so let's add 11 to the queue and let's set it to visited. 12, we've already we haven't searched 12 yet, so let's add 12 to the queue. All right, and we move it from we set it to visited. All right, and that's all the adjacent vertices. And we start over again, going to 8. 8. Let's go back to the same cycle. It can only go to 4. 4's already been visited. There's no point in adding it to the queue. We're kind of done. We're done. 9. 9, we can only go to, 5. We've already visited 5. So there's no point of adding 5 again to the queue. So we're done with 9. 10, the only vertex I can go to is 5. And I've already visited 5. There's no point of searching 5 again. So we remove it from the queue. 11, so we're searching through 11, remove it from the queue. We check, okay. I can go to 7. I've already visited 7. There's no point of adding 7 to the queue. So I'm done. And then 12, same idea. And we've finished searching through the whole queue. All right. And look at that. If we look at the queue, it's in the exact same order as I've written it. And that's why queues work, and that's how BFS works. And the searches in this chronological order. All right. And then we can create an implementation to find the shortest path between 2 vertices on a graph. So let's create a fictitious graph, and let's say you want to get from this shortest path. You want to find the shortest path between nodes. All right. So first we import queue, and I just set up variable. So n equals 15. So that's the number of vertices on this graph. And let's say we want to start on vertex 4, and we want to end at vertex 7. All right. And then I created this graph, so it has all the data, this adjacency list of all the graphs here, of all the vertices here. All right, and we create this queue, and we add, our starting position. So we start at 14, and with finding the shortest path on an unweighted graph, we also want to keep track of how many steps it takes for me to get to a location. So to start, it takes a distance of 0 to get to the starting position, since you're already there. And we also set the visited stuff to false, and except the starting position to true. All right, and it goes back to this whole idea of BFS, where we check, hey, is there any more vertices to search for? And then if there is, we grab the first item in the queue, and we check, is this equal to the end of the vertex of the destination we want to go to? And if it is, in this case, we print out the distance. So the second number here stores the distance, and we break it. And I'll get to how we got to that distance. So we go through and all adjacent vertices, and we set it as true. All right, and we do the usual stuff of putting the vertices into the queue, the adjacent vertices into the queue. But we add the current distance it takes to get to the this current vertex plus 1, since that's how we look at it. Let's say we were looking at this graph here, right? It takes a distance of 0 to get here, all right? And to get to any other vertex in this graph, we can see, okay, here, it's just a plus 1 here, so we just add 1 into this graph. And to go down here, it's a plus 1. It's another plus 1. And so on and so forth. And that's why we do like plus 1 here, since it just takes, if we haven't visited a graph, that means we haven't known the distance. And to know that distance, we just add 1 to the distance it takes to get to our current location. Does that make sense? So, and that's just to keep track of the distance from for the path. All right. So that's the idea of BreadthFirst search. Does anyone have questions about that? Does
So how do you determine if what adjacent vertices a vertice has?
so that depends on your graph, and you'll need to get input for your graph for that. So it also depends on your representation. So for edge list, it's really hard. I mentioned in my previous lesson, it's really hard to know what's adjacent to what, since you're only just keeping track of the edges. You're not really keeping track of which edge corresponds to what. With adjacency matrix, it's a bit more easier. You can just loop through and see which what's adjacent to what, since you can just loop through. Hey, is there an edge that exists between I and J? And then with the adjacency list, it's really simple. You just have to loop through all the values at that given list, adjacency list. Does that make sense?
Yeah.
So it just depends on your representation. All right. Does anyone else have any other questions? I don't want to have to, it's better for me to re-explain now rather than having to re-explain later, since it's much more fresh in your minds. No one has questions. All right, I'll continue on.
Oh wait.
Yeah.
Sorry.
Yeah, go ahead.
So in the example you gave, did you base that off a representation of a graph, so for example, an edge list?
For this example where I'm showing,
Oh.
there's a graph right here. So this is the adjacency list. So here, 0, this adjacency list. So 0 is connected to 2, 4, and 5. 1 here is connected to 5, 4, and 7. 2 here is connected to 0 and 4 and 3, and so on and so forth. Does that make sense?
Yeah. Okay.
So yeah, so that's where my adjacency list is created from. It's from this graph up here. Does anyone have any other questions? No? All right. So moving on, beyond breadth-first search, we have depth-first search, where rather than searching all the vertices at the same depth in BFS, we like to search the deepest nodes first in deepest nodes. Where, as the name implies, it's depth first search. We're trying to go the deepest. So let's say we have this graph again. All right. So we have a graph that looks like this here, and then we go back here. All right. We have this graph again. So with breadth first search, we go like each step at a time, right? But with depth first search, rather than doing that, we'd like to go we'd like to go the furthest path. So we go down here, then we go down here, then we go down here, 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 here. All right? We like to go down first rather than going like a massive breadth of vertices. We're trying to go the deepest route. All right? And this is a visual of representation of depth first. So rather than doing like 1, 2, 3, 4, so on and so forth, we go like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? So, you can see the order goes down each path rather than going level by level. With the questions I will be assigning, and with CCD Junior, there is really no benefit in using BFS over DFS or DFS over BFS. They're about the same. However, as you start doing more complex graph theory, so stuff in senior, DFS will be extremely useful. So, to implement this, we'll have to talk about a stack, which is different from a queue. So, with DFS, you'll need to learn what a stack is. So as a stack, as the name suggests, is like, a stack in real life. So like similar to how like, a queue is like in real life, we have a stack. So let's say we have a stack of paper. And let's say we're all, not trying to be funny or like not trying to be, funny in any way. How would you, add papers and remove papers from a stack? Anyone? How would you add or remove papers from a stack? From like a stack of papers. Let's say I give you like a stack of, questions to do. Like a stack of questions, I printed them out and I hand them to you. How would you remove a paper and add a paper to the stack? Place it from the bottom. So you're gonna lift up, Joanne. So you're gonna lift up the whole stack so that you can just put a paper underneath to remove the pit to put back the stack. Yeah. So everyone would place it on the top and then remove a paper from the top. And that's how a stack works in computers, and that's how the stack data structure works. And it has the principle of last in, first out, where the last item the most recent item you put in is the first item you take out. And that's a name last in, first out. So let's say I have like a stack of papers to you, and I have more questions to give you. Like let's say I throw more questions at you. You slowly do the questions that I most recently gave you from the top of the stack, and that's the idea of last in, first out. Right? And we can imagine it like this. We can visualize this here. So we have a stack that we put on top, and then we remove it from the top. All right. And to use a stack in Python, it's the same thing as creating a queue, but instead of doing queue.queue, we would use queue.LIFO-queue. So last in, first out queue. I don't know why they didn't name it stack, but they just named it the last in, first out queue. All right. Diving a bit deeper into a stack, you may remember how recursion works and how it goes in an order similar to DFS. So every time you call a function, it adds the function to something called the runtime stack, where it will try to complete whatever's on top of the stack until it's finished, and it will remove that function from the stack and continue on until the stack is empty. All right. So let's say we have this code here. All right. How do you guys think this code will run? Which will print first, guys? Test or hello world? Let me make a poll. Actually, let me just make a poll. So, let's see. Which will print first? Hello world or test? So react to whatever you guys think is the right answer. Don't be shy to make a guess, I guess, if you guys are unsure. So everyone is saying test, and that is correct. So test is the first thing that will run first, since how the runtime stack here. So if you guys read ahead, then kind of cheated, but oh well. So how it works is that in a stack, so we haven't called these functions yet. All right, we called function. We'll call function. All right. So let's create the stack here. Okay. So let's have like let's have a stack. All right. And in a stack, we called function. So we add function to the stack. All right. In function here, we called function one. So we add function one to the stack. So we have to do whatever function one does. And in function one, it calls function three. So we add function three to the stack. All right. And in function 3, it calls function 2, right? Now, function 2 is on the top of the stack. Okay, it goes first. Okay, function 2. All right, we'll print, we'll print test. And that's the end of the function. Okay, we can remove it from the stack. Okay, function 3. Okay, function 3, we've added to the stack. Okay, we're done with this function. Okay, so we remove it from the stack. Okay, now we'll go back to function 1. Function 1, okay, that's the end of the function. We can remove it from the stack. And then function. Now function. We have one more bit of thing to do, which is print hello world. Okay, so we print hello world. So it prints hello world at the bottom. And then it finishes the stack. And that's the end of the stack. All right. So that's how, this runtime stack works. And it's similar to the questions we did earlier where it was like creating a bunch of binary numbers or whatever, given with a number of bits. So it uses the idea of the runtime stack. All right. So there are multiple ways of implementing the DFS algorithm. So one way involves using a stack directly. So initializing a stack and then adding the values to the stack. Or you can use another way where you can use the runtime stack, recursive. Without going to specifics, we'll need to know the same information as BFS. All right. So this is how a recursive DFS algorithm looks like. So we first have to still initialize the visited vertices, the vertices will not be visited or not. All right. And then in this recursive function, we have to check the current vertex we're searching for, and then the destination, the vertex that we're trying to go to. All right. And we have to check. Okay, we set the vertex that we're currently visiting as true, since that's the vertex we're searching. All right. And we check, hey, is this vertex is this the vertex the destination? And if it is the destination, there's no point in searching anymore. We can just continue. We can just stop. All right. And we just go through all the vertices that are adjacent to a given vertex. All right. And looping through all the adjacent vertices, similar to how we did it in the previous lesson, the previous for BFS. And we check, hey, have we visited the adjacent vertex, and have we not visited the destination? Because there's no point of continuing to search once we visit the destination. And there's no point in searching if we've already visited this given vertex. All right? If we haven't, then we can recursively call DFS adjacent vertex destination. And it has a similar idea of like the stack here, where it just adds this item to the stack. All right? And then for iteratively, it's exactly the same as BFS, except that we just changed the queue. And that's about it. Changed life queue to life queue. That's exactly the same. And they work exactly the same where in as BFS. So let's DFS this stack this tree here, right? So we have from 1 we go to 2 to 3 to 4 or let's actually I'll just do it in the order of like this. 5 6 7 8 9 10 11 12. All right, so we have this tree here. Okay, so first in the stack, so let's do it recursively. So first, let's start by searching 1 here, all right? And there's no destination. Let's say we have no destination, all right? We set this to true, so we visit this true to true, all right? And then we loop through all the. So this is like the top of the. This is the. Let's imagine a stack here as well. So we have DFS. So we have DFS at 1, all right? Now we loop through all the adjacent vertices, and we check. Hey, have we visited this vertex before? Oh, we haven't? Okay, let's search through it. Let's add it to the stack. So DFS2. All right. Now we check through 2 now. Okay, 2. Let's loop through, we set it to true, and we loop through all the adjacent vertices. Okay. We haven't searched through, we have searched through 1, so there's no point of checking 1 now, but we haven't searched through 5. So let's DFS 5. Okay, in 5, here, we can check. Okay, we set this as true, we set it to visited, and we check all the adjacent vertices. So we check 2, okay. 2 we visited, there's no point of searching 2 again. Now we check 9 or 10. So first, so we go in order, so let's do 9. So let's DFS 9, all right? With DFS 9 here, we check, okay, all the adjacent, we set this to visited, and we check all the adjacent vertices, okay? But we've already visited all the adjacent vertices, so we can just remove this from the stack now. So this is removed from the stack, and now we go back up to the next level. So DFS 5. So we check 9. We haven't completed this loop, so we check 9. Now we check 10. Okay, now we DFS 10. And then DFS 10, we set it to true. We check all the adjacent vertices if they're visited, and if we haven't visited them, we check those, but there's no more to check. So we just exit out of this loop, this stat. We finish this function, all right? Now, 5, we've already searched through all the vertices, adjacent vertices, and we're done with this function. So we've moved from the stack as well. Okay, now back to DFS 2. So we're only halfway done this for loop, right? We haven't checked this vertex yet. So we'll add that to the stack. So DFS 6. Okay, DFS 6. We set it to true. We check all the adjacent vertices. Oh, we haven't checked. We have we've searched through all of them. Okay, we're done with this function. We remove it from the stack. 2, we've searched through all the vertices, and we're done with this function. We can remove it from the stack, and so on and so forth. And that's the idea of recursive with this recursion. And it's the same idea with adding a stack as well. So like if we just had a stack, let's say we had a stack, right? So let's start from the from the back. Okay, so we add 2, 3, 4. Okay, and 2 we add 5 and 6, and then 5 we add 9 and 10. So 2, we're searching through 2, things like that. Then we search 5, then we search 9, then 10, then 6, then 3, and so on and so forth. And that's the idea of a stack as well. So you'll notice the iterative way of DFS is it's very similar to BFS, and you're correct. The only difference is we're just using a stack instead of a queue. So using the following graph, we can check if it's possible to get from one location to another location using DFS. So we can DFS this graph, I guess, using DFS. So I'll use the recursive way, and we just check, hey, if we visited a location. All right. So does anyone have questions about DFS?
So basically, BFS and DFS use different kinds of queues.
Yeah. So it's not really queues. Well, the stack isn't necessarily a queue, but they use different data structures, pretty much.
Okay.
And it's just a different order of searching, pretty much. That's the difference. It's a different order of searching. So DFS, you search the deepest. Try to find the deepest node node vertex first, while like the furthest one, while BFS it tries to search one distance at a time. Does that make sense? Is there anything a bit more confusing about it, or uh
No, it's good.
All right. So the differences between BFS and DFS is that there isn't really much differences except just how they're searching. In terms of time complexity and space complexity, they have the exact same time complexity and space complexity. So the worst case time is that it's O at V plus E, since you're always searching all the vertices and you're also searching all the edges. So um, that's the worst case time. And the worst case space complexity is O at V, which is the number of vertices. And for the questions we will be doing for junior CCC and junior CCC, there is no, as I said earlier, there's no advantage or disadvantage to using one or the other. However, they will branch off into separate algorithms that will be useful in the near future. So for junior CS club, we'll be primarily looking at algorithms derived from BFS, while senior will be looking at algorithms derived from DFS. Doesn't mean you should primarily focus on one or the other. Rather, you should know both no matter what. And note that I've only shown you code so far. The code that I've shown you so far are just generalizations of the algorithms. Every single question, I guarantee you not, will have you encounter a question that will have you encounter that you'll encounter will have you manipulate these algorithms to solve them. All right. So beyond looking at graphs, we can look at grids, which is pretty much it's just a graph, right? And it's instead we just look at like each cell of the grid is a vertex, and there are edges between every single grid in every cardinal direction. So you can go up, down, left, right. And we can use BFS and DFS to search a grid with this idea. So like if we had a grid, so let's say we have a grid, right? Right, we have a grid here. If we start in this location, we can imagine that there's just edges between each of these locations, each of these grids in each direction, right? So you can go up, down, left, right. And we can use the idea of BFS or TFS to search through and searching through every single grid. So each of these cells is like a vertex, and each direction is like an edge. Once you get to this, like to a corner, to these edges here, like of the grid, you can only go in certain directions. So we can use BFS or DFS to search a grid with this idea. And this also allows us to do something called flood fill, where you can fill any multi-dimensional array with any information. And all we need to do is just add an additional step on top of visiting a cell to changing it to what we want to fill the cell with. And that's about it. That's the only difference about that's what flood fill is pretty much essentially. All right. And that gets us to the end of today's lesson, of this week's lesson. So, does anyone have questions about what I just taught so far? What about BFS, DFS, grid searching, and flood fill? No one has questions. So you guys will be able to do all these questions here?
Well, like, I don't know, like for me, I don't have any questions. Like, I just feel like I might need to if this gets uploaded, I'll probably need to just rewatch it. Like, it's like what I think
You just need another you can like a
Dorothy
like
said, like I'm confused. I'm just not quite sure what I'm confused about. Well,
that's no worries.
no.
If anyone has questions during the break, feel free to message me. And just don't save your questions for ComSci Club. Send me your questions as soon as you have them. Because I will guarantee you guys will forget your question. And even if I'm busy, like, let's say I'm running a test, I will look at your question after I'm done, and I will help you. All right. So, just keep that in mind. So, if no one has questions now, but you guys are confused, just do let me know. Since I expect you try to do at least a few questions. So this first question here, I expect everyone to be able to at least do it. Since this is just simple BFS TFS. So it's just checking if it's possible to go from one location to another location. So, if you guys don't want to do all the questions, that's fine. I just expect you guys to be able to do this first question, and that's about it. All right. Other than that, no one has questions? Going once? Going twice?
Um, actually, like, um, maybe, oh, like, would you mind like uploading like maybe a separate video of you doing one of the problems? So like that way, if we get stuck, like we could like watch and see how to,
All right,
or
I'll try to do something like that during the break. I might
okay,
forget, so can someone please remind me?
okay,
All right. But yeah. If no one has questions, heck, would you guys want this? So I might be able to, I can set up a day where I can just take up questions like live, I guess. So you guys can look at me, look at what my thought process is while I'm taking up the questions, so that you guys don't have to be confused while I'm, I'm taking up the questions. How does that sound? I'll just make a poll for that. Um, so I'll create a poll. So would you want a day where I set a day where I uh, I take up some questions and answer um, other questions about graph theory during the break. And of course, I'll be recording that uh, lesson as well, that take up day. So, would anyone want that happen? You don't have to answer that now. I'll of course look at it later. But other than that, if no one has questions for today's lesson, I guess um that's ComSci Club for this week. Um, someone posted something in Junior. It doesn't have to be. Yeah, it doesn't have to be all the questions. I can take up. Well, I can take up some of the questions. I'll leave some questions for me to take up at um when we come back. But other than that, if no one has additional questions, then I think we can call it a day here. Thank you everyone for joining me today. And yeah, have a nice break, I guess,